All right, guys, to get you ready for the start of Unit 2, which we will be tackling on Monday, we want to get you going on just some of the basics of working with rational numbers. Unit 2 is all about rational and irrational numbers along with the rules of exponents. And we've talked about this a little bit in the past, and we'll talk a little bit more about in class about what rational numbers are versus what irrational numbers are. By the end of this unit, after we've answered the essential questions of Unit 2, we'll also be able to get this joke, and you guys won't think I'm just a big, giant math nerd. But for now, what we just want to make sure we understand is the very basics of rational and irrational numbers and how they compare. Rational numbers, by definition, are numbers that can be written as a quotient of two integers. When I say quotient of two integers, I'm thinking they can be written as a fraction. When written as a decimal, they either terminate or form a repeating pattern. 99% of the numbers that you see are rational numbers. Those are the numbers you're used to working with. Irrational numbers, on the other hand, cannot be represented as a quotient of two integers. When written as a decimal, they are never ending and not repeating. Your favorite, best example of that would be pi. As I write that as a decimal, it never ends and it never forms a repeating pattern. The big thing they have in common, the number one thing you got to understand, is both are considered real, which we'll come back to when we get to the point of that joke you saw on the first slide. For Monday, what I just want to go over some basic understandings of some of the things that we should know as far as working with rational numbers. A lot of these are your background knowledge, and we should have some working background knowledge here to tackle these problems. It says, show the numbers rational by writing it as a quotient of two integers. When I hear quotient of two integers, I'm thinking I want to write this as a fraction, as some number over some other number. Now notice, they have to be integers, which means I can't have a fraction or a decimal in the numerator or denominator. I just have to have integers for a numerator and denominator. 7 would be the simplest one we've probably worked with in this case. 7, to make that into a fraction, well, what would I put that over where I don't change the value of that number, but I do write it as a quotient of two integers? In this case, it would be 7 over 1, because 7 divided by 1 still has that same value of 7. Same thing works for a negative number. Negative 10 over 1 is still worth negative 10, and we have proven that it's rational by writing it as a quotient of two integers. Might be a little trickier, but in your background knowledge, we should remember how to do this with a mixed number. If I have 5 3/4, recall that we've talked about this in the past, and we've said, well, I will take the numerator and add that to what the denominator is times the whole number part. So 4 times 5 is 20. Add that numerator to that, and I get 23 for my numerator, and I put that over whatever the denominator was initially. If I carried this division out, I would get back to that same idea of 5 3/4. And so by writing it as 23 over 4, we've proven that that number is rational by writing it as a quotient of two integers. Another thing we'll see it the other way, essentially. We'll see fraction that will tell you to write it as a decimal. Remember, to do this, we can see that fraction bar as a division bar, and we just need to do a little division. Take the top divided by the bottom, 3 divided by 8. Because we're going to be writing them as a decimal, you should expect to have to do a little bit of the fancy decimal division. Add a decimal point, add the zeros. Your decimal goes straight up top. Make sure your answer makes sense. 3/8 is clearly less than 1, so I need to make sure that my decimal number is less than 1. That means I'm going to have a 0 first, and then I'm playing the game of, well, how many times does 8 go into 30, and I'm going to continue to do the division that you're used to from long ago. Just double checking ourselves and making sure that we can do that decimal division, and I see that 3/8 as a decimal number is 375 thousandths. Both of those, of course, would be rational numbers because I can write them as a quotient of two integers. Same works for 5 11ths. Again, it's numerator divided by denominator. Something tricky happens here a little bit, though, actually, as I add zeros and see what's going on. Again, it's less than 1. It's just right around a half, so I know I should have 0 the first time. And then I'm saying 11 into 50 is 44, and I'm going to play this game where I do a little division, and hopefully, while you're working this at home, you see what I see, and that's I see a pattern. And again, because this is a rational number, as we discussed, it can happen. A rational number is going to do one of two things when written as a decimal. It will either terminate or form a repeating pattern. The first example here terminated, 375 thousandths. This second example forms a repeating pattern, so remember to write that as a decimal. We take that repeating pattern and we put the bar over the numbers that repeat, and now I've written that rational number as a decimal. Next type of problem we see is the terminating decimals as a fraction. So I give you the terminating decimal, and I want you to write that for me as a fraction. Very, very basic rule here that we've talked about in the past. If you can read it, you can write it. Then you might need to reduce it. When I see this first number, I see, yes, 0.7. But if I could read it correctly, I would see, well, that's 7/10. And notice now, I have proven that that number is rational by writing it as a quotient of two integers, or writing it as a fraction. The same would hold for a mixed number. In this case, I have -3 and 5/100ths. Now, a couple things I need to do with this mixed number. First of all, like I've told you, for the rest of your time on this earth, until you get to the pearly gates, we're going to have to reduce fractions. So the first thing I'm probably going to look at is I'm going to say, well, this is actually going to be the same thing as -3 and 1/20th as I reduce that part of the mixed number. Second thing I noticed is I want it as a fraction. I want it as a quotient of two integers. So now we're back to making mixed numbers into improper fractions. 20 times 3 is 60, plus 1 is 61. So notice I have 61 over 20, but then as Mr. Bartlett would tell you repeatedly for your quizzes and tests, make sure your answer makes sense. Because we had a negative number to begin with, that number still needs to be negative, and now we've taken care of that. Last examples are probably the trickiest, but again, it's a very simple rule if we think about this. To write a repeating decimal as a fraction, the tip is to put the block of repeating digits over 9, or in some cases 99, or 999. That's what the S in parentheses means. It's the number of digits need to have that many number of 9s. However many repeating digits you have, you're going to have that many 9s. Put it into a mixed number, or put it into a fraction, and then simplify. For example, I see two digits that repeat here. The 9 and the 3 repeat. If we expanded this out, we would have 0.93, 93, 93, and so on. I'm going to take those repeating digits, the 9 and the 3, and I'm going to put that over a block of 9s. If I had one digit, I'd have 1 9. If I have two digits like I do here, I'd have 99. I have 93 over 99, and the only thing that I would need to do now is reduce that fraction. Both of these are divisible by 3. I can tell that. If you recall, I look at the top number, and I see, well, 9 plus 3 is 12. And 9 plus 9 is 18. Since 12 and 18 are both divisible by 3, both of these numbers are divisible by 3. That gives me 93 divided by 3, which would be 31, and 99 divided by 3, which would be 33. And now I've actually written a repeating decimal as a fraction. 2 and 6/10 repeating. Notice there's only one repeating digit, so this would be 2 and 6 over 9. I only need the 1 9 because I have the one repeating digit. Same rules apply. Need to reduce, and then of course need to make it into an improper fraction to prove that it is actually a quotient of two integers, where we keep coming back to that same idea of A over B. We'll spend a lot of time in class actually discussing rational and irrational numbers and making sure we understand their definitions and the examples of which, so we can talk about that on a test or a quiz or even in an essay in a journal. But what you really need to know are just the basics of working with rational numbers, and this video should take care of that.